Welcome everybody. It is my great pleasure to
Welcome
welcome
everybody.
you to the 7th edition of the International Conference on Cryptology and Information Security in Latin America, LatinCrypt 2021, splendidly organized by Universidad del Rosario in Bogotá, Colombia, and in cooperation with the IACR. So we started back in 2010 with the first LatinCrypt conference in Puebla, Mexico. And after that, 2 years later, we had the second conference in Santiago, Chile in 2012. 2 years later, it was the turn for Brazil with LatinCrypt 2014 in Florianopolis. The next year, it was the second turn for Mexico in Guadalajara 2015. And 2 years after that, it was the turn of Havana, Cuba. In 2 years, again, the second opportunity for Chile, we have LatinCrypt 2019. And now this year, it was the turn of Colombia with Bogotá 2021. And while many of you probably are going to miss the Latin dances or maybe the heavy drinking of tequila of past events, for this year, we have assembled a marvelous program. You should recognize our stellar keynote speakers. Later today, we will have Luca Di Feo, who is going to talk about what's next for ISO-based cryptography. Tomorrow, on Thursday, Shweta Agrawal is going to cover recent progress and challenges in lattice-based cryptography. And for the grand finale, Dan Bonnetain is going to talk about recent developments in cryptography on Friday. So again, a great program not to be missed. Now let's talk about a little bit about the statistics for this LatinCrypt. We had 47 papers submitted from 26 different countries. The number of accepted papers, 22, from 17 different countries. From all these 22 papers, we had 64 different authors. 7 of these authors have Latin American roots, and they are co-authoring up to 5 papers. And now 2 papers have Latin American affiliation. We have to thank our reviewers and external reviewers. We had a wonderful program committee, 43 reviewers, and also the assistance of 28 external reviewers. So thanks again for the great work that they put on this conference and reviewing all the papers. Now you can see here in this graph the split of the papers according to the authorships of papers accepted per country. So on top we have Canada, followed by Denmark, France, Germany, Belgium, India, United Kingdom, United States, Chile, China, Israel, Malaysia, Mexico, Norway, Sweden, and UAE. Now, until yesterday that I put together these slides, we had 143 people register. All of you are coming from 24 different countries, covering 5 continents. And here is the split up of the register people by country of affiliation. So we have Colombia at the top, but followed by United States, France, Chile, Spain, UAE, India, Brazil, Canada, Cameroon, Denmark, United Kingdom, Ecuador, Uruguay, Netherlands, Mexico, Germany, Israel, Argentina, Switzerland, Sweden, Peru, Norway, and Belgium. Regarding institutional participation, according to the number of participants coming from different places, some different institutions, we have Universidad del Rosario of Colombia on top, of course, followed by Technology and Innovation Institute from UAE, and in the third place we have University of Chile from Chile, of course. And honorific mentions, we have Argus University from Denmark, University of Campinas from Brazil, and also University of Waterloo from Canada. And with that, I want to pass the microphone to Valerie who's going to talk about social events and navigating the Latin Crypt website.
Thank you, Patrick. Hello, everyone. I'm very happy to be the General Chair this year of Latin Crypt. Thank you to the steering committee and Francisco, especially for inviting me for this organization. So if you go to the next slide, if you can see that here you only can make questions to the moderator, so they will go and ask the questions to the authors at the end of each session. So we have all the presentation, and at the end we will have this question and answer part. But if you want to speak more with the colleagues and do the networking part, please go downstairs to the left. You have this networking button. You can just click there, and then you can, in the next slide, please, you can just chat with the people who are in the group of Latin Crypt, and you can also have video calls and talk together, or you can also create some groups in the top part. You can create a private group. For example, if I want to talk with Carla and Patrick, we want to create a private one. But then if we want to have a public one about quantum cryptography, we can create one, and then the people can go there and talk about certain topics, or PhD students, for example, opportunities. So be free to create your own groups and profit to do all the networking that you can do in a virtual way, while we came back to the salsa and tequilas that Patrick missed already. If you go to the next one, please. When we are at the Universidad del Rosario, as Patrick says, so welcome everyone, even if it's a remote way. If you click in the statue, you can know more about the claustro, that is the place where you are in a virtual way, that is the main campus of our university. In the left and the right part, you can have the auditorium that you already found out. You can, if you already explored the platform, you can go upstairs and just click auditorium and you will arrive. And to the left part, we try to recreate Café de Colombia, like a traditional house in the coffee region, that if you go there, you can explore the social events, and you can explore also more about Colombia. And if please click, Patrick, you can also have a picture like the one of Francisco already made, and publish it in the social networks like Latin Crypt 2021. And so next one, please. We will have two social events where we will do it through Google Meet, so you will be able to chat with other people also. One of them is a virtual tour to a traditional Colombian coffee farm that is tomorrow at 2 p.m. Colombian time. So please go there. And the next one, please. We will have, it's really early for Colombian people and more for Patrick in the Pacific time, right? But I think it's very good time for Europe. You can go from 6 a.m. of Colombia, and we can see the waking up in the Colombian coffee region. It's we will see the birds of this part that they will go and on live, they go and eat, and we have some hidden cameras, and we can see how the birds interact. So I hope you enjoy them. If you click, please. You can explore the platform, but if you are in a hurry and you just want to go to the events, you can go to the menu and click directly to the auditorium or to the House of Colombia or to the social events. I hope you really enjoy the platform, the conference. I want to thank also all the authors that sent the papers. We are very happy with the numbers of assistants. And if you have any question, you all have received an email from me. So please send me an email and I will be happy to answer. Carla, you wanted to send a message?
No, I just want to welcome everyone, and I'm looking forward to the talks. So
Great. So let's start with the first session, right?
Yes.
Yes, excellent. Yeah. So the first session is gonna be quantum algorithms, and it's gonna be moderated by André Schrottenloher. So we can start already with the marvelous program.
Thanks, Patrick. So this first session of Let Encrypt 2021 is about quantum algorithms. And we have three talks, two presentations recorded and one live. The first one is going to be tight bonds for Simon's algorithm. The talk is given by Xavier Bonnetain. Xavier. What is yours?
Okay. Can you see the slides? Or should I? Okay, perfect. So thank you all for being there, and welcome again to Let Encrypt. I will present my work, type bound for Simon's algorithm. So first of all, I will present the algorithm we'll study in the presentation, Simon's algorithm, then explain what happens in a common scenario in quantum cryptanalysis, where Simon's algorithm has to deal with additional collision, and finally I will present my results. So first of all, Simon's algorithm. This algorithm aims at solving a very specific problem where you have a function f on n bits, and this function has a peculiar property of being periodic and 2 to 1. That is, for each image of the function, you have exactly 2 preimages, and the XOR of these 2 preimages is a fixed value s. S is the hidden period of the function, and you want to find it. Classically, this problem reduces simply to collision finding. The best you can do is to get to the n over 2 samples and look for a collision. Quantumly, we can do much better with Simon's algorithm, which only requires a linear amount of quantum queries plus a small classical post-processing. So in more details, how does this algorithm work? It's quite simple. You start with 2 quantum registers that we can initialize at 0. Then we apply a Hadamard gate on the first register. This allows us to produce a uniform superpositions of all the possible values in this register. Then we apply a quantum oracle to the periodic function, which allows us to compute the uniform superposition of all the input-output of the function, of all the tuples. Now we measure the second register. This allows us to get a random image of the function, and f of xo for a random input, and it will project the first register on the values that are compatible with what we measured. That is, thanks to the promise, we'll have the superposition of these 2 values here. So at this point, if we measure the first register, we wouldn't have achieved anything. It would be strictly equivalent to sampling a random value and then computing the image through the function. Now, the real quantum engineering part comes there when we reapply a Hadamard gate on the first register. And here we will get 2 components that come from the 2 components at the previous step, and these 2 components will interfere. And if we rewrite the state that we have, we can see that it is a superposition of states, and the y's we have in this superposition have a non-zero amplitude if and only if they are orthogonal to the period. This means that Simon's circuit allows us to uniformly sample values that are orthogonal to the period. So now from that it's quite easy to recover it. So I recall here the problem. Remember that Simon's algorithm uses superposition query, that is the ability to compute, given the uniform superposition of all its possible input, the uniform superposition of all the input-output tuples. And this is what we mean when we say that Simon's algorithm is polynomial. It's polynomial with these queries and not classical queries. So from that, we sample uniform values that are orthogonal to the period, and then it's simply a linear algebra to recover the period. So now, how can we do cryptanalysis from that? The general idea is quite simple. We manage to construct a periodic function from a given cipher whose period is something of interest, typically a secret key or something else. And it has many applications. We've seen in the literature many quantum distinguishers, typically on phase-tail and generalized phase-tail constructions. We have some key recoveries on various constructions, for example, even Mansur that we'll see later, or the FX constructions. And we can also do forgeries on many efficient modes for authenticated encryptions. Typically, most modes with birthday-bound security and a few others are affected by these kind of attacks. So, for example, what does this mean? I will present now a quantum attack on the even Mansur cipher. So, this cipher is a very simple block cipher. Some say the simplest. To encrypt a message X, you simply apply a first key, K1, then you XOR a first key, K1, then you apply a public random permutation P, then you XOR a second key, and you get your ciphertext. And this simple construction classically is proven. That is, it has been shown that any attack requires an amount of time and an amount of data such that the product of the two is at least 2 to the n. Now, quantumly, it's quite different, because if we consider the encryption of a message X, and we add to that the image by the public permutation of the same X, we have a periodic function. So it's fairly easy to see. We have here the addition shown by 2 branches. We can first push forward the second key because it commutes with the permutation addition, and then if we add the value K1 to the input, it's easy to see that if we push it forward, it will simply amount in swapping the 2 branches, so it does not change the output. This means that we have a periodic function whose period is the first key of the even Mansur, so we can apply Simon's algorithm to recover it. However, there is one limitation, because what I presented here is not a function that satisfies the promise I presented earlier. That is, we have a periodic function, we have a period, but we do not necessarily have a 2-to-1 function. We have no reason for that, and we may have some input who collides on the same output, but whose XOR is not the period K1. We may have more preimages than only 2. And so now I will present what happens in that case. So what happens with Simon's algorithm with additional collision. So in general, in cryptography, we have this more general problem, which is a less restricted version, where the only thing we're guaranteed is that we have a period, and we do not have any other constraints. And if we apply Simon's algorithm on such a function, then what will happen is that the good news is that the Simon's algorithm is still correct. We will still only sample the vectors that are orthogonal to the period. The bad news is that these vectors are no longer uniform, they are biased, which means that we still have a correct algorithm, but we may have a much slower algorithm. And the question is how significant this increase in complexity is. So, for example, we can see what happens in some very bad cases. So here I have the example of a function which is all 0 except for 2 values, 0 and s. And it's fairly easy to see that this function has a unique period, s, which means that Simon's algorithm should be able to recover this value. However, it turns out that this periodic function can be computed from any function that outputs a unique one. So typically, any predicate that is fulfilled for only one input. And this is annoying because this means that we can reduce unstructured search with one solution to period finding, which means that because we have a lower bound on the quantum algorithm to solve unstructured search that Simon's algorithm can't be efficient on such a function. We can't even expect it to be sub-exponential because the lower bound actually matches Grover's algorithm. This means that there exist some functions for which Simon's algorithm is absolutely not efficient. But the question is, what happens in typical case? Because the function I presented here is not what we would expect in a cryptographic context, because it's extremely degenerate cases with only two outputs and it's almost constant. So how this issue was dealt in the literature when we have additional collisions? There has been many approaches. The first one, that is more in the earliest papers, was simply not to mention it and not really take it into account and only focus on the periodic property for the cryptanalysis. Then we can have also some approaches with some hand-waving and no real focus on concrete complexity and simply claim a polynomial complexity, which is more than enough to claim that the cryptanalysis is efficient. We also have some other approaches. For example, we can try to remove the additional collisions on the function. So instead of considering f of x, we will consider the concatenation of, for example, f of x with f of x plus a constant and so on. And at some point, this will remove any collision in the function at the expense of, instead of doing one query per application of Simon's algorithm, you will do multiple queries for that. There has been some other approaches. For example, in an article by Kaplan, Laurent, Leverrier, and Naya Plasencia, they show how we can upper bound the cost of Simon's algorithm by leveraging some differential properties of the periodic function, which means that if you want to apply that, there is some sort of work to show that the studied periodic function has the required differential properties. And finally, there are also some approaches where we assume that the periodic function has been sampled at random, which also allows to get some concrete cost estimates. However, in general, with these approaches, this has the limitation that either it's not that rigorous in some cases, and in all cases, we won't really have some precise estimates because we tend to get some loose bounds, which is not really practical if we, for example, if we want to get some complete cost estimates for a full quantum circuits in similarly to what we have, for example, for Shor's algorithm or for quantum search on an AES key in symmetric cryptography, for example. So this is because this situation was not really satisfactory for me that I decided to obtain some much more precise estimates for Simon's algorithm, especially in the case where we have additional collision, which is a common case in cryptanalysis. So here is a summary of my results for plain Simon's algorithm when we have a black box periodic function. So the ideal case is fairly simple. We have an average cost of n plus 2 queries, and we can also show that with n plus a constant number of queries, we have a success probability which is in inverse 1 minus an inverse exponential. And what I've shown is that for almost all functions, we can get the same success probability as the ideal case, but at least the same success probability by adding one query. Which means that for almost all functions, this additional collision essentially change nothing because it's at most an increase of 1 in the number of queries. And by almost, I mean all but a fraction, which is an inverse of a double exponential. So it's really almost all function, and the bad cases that we've seen earlier are really extremely rare in practice. So this was for plain Simon's algorithm. Now there are some other ways to use it, and especially we can do cryptanalysis by using Simon's algorithm in a quantum search. There have been two algorithms that do that. The first one is the Grover-Mitz-Simon. So it aims at solving a different problem. Instead of having one periodic function, we have a family of functions that are indexed by a key, k, and we know that for one of the key, the function is periodic. And we want to find for which key this function is periodic. And so the Grover-Mitz-Simon algorithm that has been presented by André and May in 2017 proposed to solve this problem with a simple idea. We do a quantum search on the key, and to test whether a key is correct or not, we apply Simon's algorithm. For the correct key, we will get a period, so we will know the function is periodic. And for the wrong key, the function will not be periodic, which means that Simon's algorithm will return the period 0. And the cost of this algorithm is the cost of a quantum search, so 2 to the k over 2 iteration, times the cost of Simon's algorithm, which is polynomial. So we still get something in 2 to the k over 2. There has been another algorithm that uses Simon's algorithm in the quantum search. This algorithm can be seen as a restriction of the previous problem. So instead of having only one family of functions, we have one family of function plus a function on n-bit input. And we know that for one key, the sum of so f of k0 and g is periodic, and we want to know for which key we have this property. So this is really a restriction of the previous problem, and the offline Simon's algorithm allows us to solve this problem as Grover-Mitz-Simon, but with the additional advantage that it can solve it with quantum access to F and classical access to G. So typically, G will be the secret cipher, and F will be the specification of it. So typically a code that takes a key and a message and encrypts it. This allows to apply some Simon-based cryptanalysis, but with only classical access to secret material. And so the cost of this algorithm is slightly different. It's not only 2 to the k over 2, it also depends on the material space, so it's a max of 2 to the k over 2 on n. And the algorithm is really the same idea as Grover-Mitz-Simon, to use Simon's algorithm inside a quantum search for the correct key. So without delving into the technical details, I managed to get some improved cost estimates for these two algorithms. For Grover-Mitz-Simon, I gained roughly a factor 2 compared to the initial estimate, so n plus a constant instead of 2n plus a square root. And for the offline Simon's algorithm, the original paper really focused on showing that a polynomial number of queries per test in the iteration is sufficient, and I managed to show that it's only n plus k queries plus a constant to succeed in the algorithm. So it's slightly worse than Grover-Mitz-Simon, but still very, very reasonable. So now that we have shown that actually in practice collisions are really not an issue and have almost no impact on the algorithm, this means that we can artificially increase the number of collisions if this is something we want to do without any really slowing the algorithm. And what we can do is to simply truncate the output of the function. And I managed to show that we can truncate the output size of a periodic function, so still for almost all periodic functions, to a logarithmic amount of bits without any noticeable complexity increase. And in practice, for parameters of cryptographic relevance, it will be around 11 bits of output. And so what this means for cryptanalysis If we have a direct application of Simon's algorithm with a black box periodic function, then it's essentially useless, because to compute a truncated function, you will need to first compute the full function and then truncate it, so it would be already over. In some cases, if you have an in-place oracle, that is an oracle that transforms the input to the output, then you can save slightly less than a factor 2 in some cryptanalysis. And the most interesting part is for reversible application of Simon's algorithm, and typically for the offline Simon's algorithm, you can save around a factor 3 using these techniques, because we have many queries that are done in parallel, and we can this way use multiple times the number of qubits we save. And so these techniques allows us to save qubits essentially for free, because we simply store less qubits in memory. So to conclude, we gave some exact query cost for Simon's algorithm with an uncertainty of less than 1 query. This shows that additional collisions for almost all functions are irrelevant in practice. This also allows us to truncate the periodic function to save qubits for free. The paper also contains some other cases, such as some recursive application of Simon's algorithm. We studied what happens with multiple periods. I also studied the exact variant of Simon's algorithm, which is unfortunately irrelevant for cryptographic applications. And as a follow-up work, this work allows to do complete quantum circuit cost estimates with time and memory estimates, and this is something that I've done with SamJax in a work that has just been accepted at TCHS. Thanks for your attention.
Thanks, Xavier, for the presentation. So the second paper in this session is Constructions for Quantum Distinguishability Obfuscation. And we listen to, so it's by Anne Broadbent and Raza Kazmi, and we listen to a talk given by Anne Broadbent.
Hi, my name is Anne Broadbent, and I'll be telling you today about constructions for quantum indistinguishability obfuscation. This is joint work with Raza Kazmi. When we talk about obfuscation, we think about hiding the inner workings of a circuit. There's a definition of obfuscation called indistinguishability obfuscation, or IO, that doesn't exactly capture this idea of hiding the inner workings, but it gets pretty close. So IO is an algorithm, and it takes a circuit and outputs IO of that circuit. And the security notion is that if the two input circuits, C1 or C2, are equivalent, meaning that they compute the same function, then the outputs of the IO are computationally indistinguishable. And that's what that figure here represents. IO has been very successful in achieving all sorts of cryptographic primitives from standard assumptions. So we have, for instance, digital signatures, public key encryption, multi-party key agreement, broadcast encryption, fully homomorphic encryption, witness indistinguishable proofs, and more. There are some constructions for quantum IO based on standard assumptions. So it's widely believed that this type of IO exists. On the quantum side, in terms of post-quantum secure IO, there are some really very good candidates, so it seems plausible. In quantum obfuscation, the objects to obfuscate can be a quantum circuit, and the output of the obfuscator can include a quantum state. So there are different variants of this, whether or not we have the input being a classical circuit or a quantum circuit, and whether the output is allowed to be a quantum state, to contain also a quantum state. So there's something called quantum virtual black box, VBB obfuscation. The topic of this talk is not VBB obfuscation, so I'm not going to go into details, but this is really the idealized version of obfuscation where it acts as a black box. And this was shown to be impossible to achieve for multi-output obfuscators. And also recently, general impossibility, showing that a counterexample for achieving quantum VBB obfuscation. And this mirrors the classical result showing that classical VBB is impossible in general, also by creating a counterexample. This talk is about quantum indistinguishability obfuscation, and the first definitions were from 2016, and ours are going to follow closely that family of definitions. This work is the first time that we have constructions for quantum I/O. So we're not going to achieve I/O for all quantum circuits. We're going to achieve it for certain families of quantum circuits. And then there's some follow-up work that shows how we can do I/O for null quantum circuits, which are circuits that almost always reject. And these null quantum circuits also have applications in terms of I/O. So the contributions in more detail, we have QIO constructions, first of all, for Clifford circuits, and that's going to be achieved using the canonical form. And we also have how to do QIO for Clifford circuits using what's called gate teleportation. I'll tell you more about this. And this gate teleportation, we can extend it to doing logarithmic number of non-Clifford gates. And then we have a different approach, which is to use known results on learning of quantum channels, and applying those learning techniques, we can get a version of a QIO for some family of circuits. So most of us are familiar with circuits. They are a logic network that compute a Boolean function. And for classical circuits, the NAND gate is universal. We have something similar for quantum circuits. By the way, in this talk, I'm not assuming that you would necessarily know background on quantum computation. So I'm trying to keep it just at the level that is required to understand what's going on, but not going into too many details. So for quantum circuits, we have something similar. The wires are called qubits. They are two-dimensional complex vectors. And then we have gates. These boxes are 1 qubit gates, which are 2 by 2 unitary matrices over the complex numbers. And we have 2 qubit gates here. It's this wire with the circle and the XOR. It's called a control knot, and that's a 2 qubit gate. So it's a 4 by 4 unitary matrix, and time goes from left to right as in the classical circuits. We also have a concept of universality. However, the gate set is much larger than for the classical case. So here's one universal gate set. We take all of these gates, which are called together, which are called the Clifford group gates. They generate a group, meaning that you can take them acting on n qubits and do any combination of these, and that forms a group. There's a subset of these called the poly gates, which are important. And there's a relationship between the n-qubit Cliffords and the poly group, namely the n-qubit Cliffords are the normalizer of the poly group. And then in order to get universality, we add a non-Clifford group gate. So in this talk, we're going to use what's called the T gate. And this one is not part of the Clifford group. And then you would get universal quantum computation, but in the most general case, we would also add single qubit preparation and single qubit measurement, although our circuits today are not going to require these. And for practical purposes, it's not, it can be useful to have these, but not actually to describe unitaries. So that's the universal quantum computation model. The definition of indistinguishability obfuscation for the quantum case closely follows that of the definition for the classical case. So first we define a family of circuits. That's calligraphic C sub Q. And then we're going to define computational, statistical, or perfect QIO, depending on the following. First of all, we have this functionality. So the output of the IO has to have the same functionality as the original input. So that's what's given by this diamond norm. And the diamond norm being 0 means that the channel is induced by the original circuit, which is CQ, or the output of the IO, which is CQ prime, together with the quantum state ket psi. Ket phi, those two channels are identical. And then we have a point 2 is a efficiency requirement, which is pretty standard. And 3 is the security definition, saying that if you have 2 quantum circuits that are equivalent, then the output distributions are respectively computationally, statistically, or perfectly indistinguishable. depending on the case. It's well known that a canonical form or a normal form is an obfuscation. It's an IO obfuscation. So when you think about it, the normal form is going to, by definition, for each circuit that has the same functionality, is going to output an identical circuit. So we translate that to the quantum case, and we know that there is a canonical or standard normal form, all the same thing, for Clifford circuits, and moreover, this can be achieved in polynomial time. So this automatically gives us an obfuscator, and any two Cliffords will have the same canonical form, and that could be our obfuscator. To go beyond Clifford circuits, we're going to look at a different way of obfuscating Clifford circuits using IO for IO that's not a normal form. So in order to explain this, let me tell you about quantum teleportation. This is a way to route a qubit ket psi from Alice, which is like at the top part of this picture, to Bob, which is holding the bottom qubit. And what happens is that they share an entangled state, which is a 2-qubit entangled state that cannot be written as a tensor product of single qubits. And that's on this left-hand side, 1 over square root 2 ket 00 plus ket 11. And then Alice does a Bell basis measurement, which is a 2-qubit measurement. It produces 2 classical bits, A and B. And then conditioned on A and B, Bob is going to apply what's called a correction, X to the B, Z to the A, and that is going to reconstruct Alice's qubit psi on the other side. And the importance here is in this correction. There's a way to think about computation as a generalization of the teleportation that we just saw. It's called gate teleportation. Suppose that you wanted to evaluate a Clifford circuit G on a qubit psi. Well, here's a way to do it. It seems a little bit roundabout, but the intuition is nice. So we can apply the circuit G, it's a single qubit, to the entangled state, so to this resource state used in teleportation. So we apply the G on the second qubit here. And then when Alice goes to do the teleportation, we will adapt the correction bits, A prime and B prime, so that they could depend on the gate G, on the Clifford gate G that was applied. So that's this F sub G. How exactly we do that? Well, if X is a poly gate, then F sub G is the same as the initial A and B. And then we'll change F sub G a little bit if it's the P gate. If G is a Hadamard, this is this H thing, then we'll swap the positions of A and B. And the idea is that after the Bell basis measurement, it's as if we had applied the gate G to X to the B, Z to the A ket psi. That's what's going on at this point here with these red dots. But really we want the G applied to the original input ket psi. So if we adapt this this poly correction based on the G, it's going to kind of commute it on the outside, and then we can correct it as in the usual way in teleportation. So that's how we can recover ket psi, G applied to ket psi. So that's crucial that via this teleportation, we've actually applied a gate. And for C0, it's slightly more complicated because you have a 2-qubit gate, but basically if you have a two entangled states to start with, and then 2 Bell basis measurements, you'll get 4 output bits, classical bits, and then you have this update function, which is defined here, and you'll also be able to obtain the C0 applied to the original input, which is a 2-qubit input at this point. We can compose gate functions in this way in order to do general n-qubit circuits. And in order to do that, we look at the different elements. I've already told you how to do the updates for all the Clifford group gates. And so for instance, the Hadamard is going to swap, and then the C0 is going to do these XORs, etc. And so if you're doing both the Hadamard and the C0, then you can compute the new function, update function for each bit here. You can compute how it is, and it's actually going to be a combination of the input of the original input bits, of course. Okay, and then the remark is that if we have two equivalent quantum circuits, so circuits that may have a different circuit representation, but that are computing the same unitary, then the update functions FCQ and F prime CQ are also computing the exact same thing. And we can look at this algebraically and see why this should be true. So, so the idea for the quantum I/O is that we're going to use this Clifford gate teleportation idea. It works for in general for n qubits, as described here. And okay, so for the I/O, here it is. We will produce, as part of the output of the I/O, is going to produce this update function F sub CQ, and apply a classical I/O to that function, which we assume exists. So post-quantum secure a classical I/O to that update function, and as well as give the state identity tensor the Clifford applied to the shared entangled states to start with. And so that combined together, these will be indistinguishable for any Clifford circuits that have the same, that are equivalent, because the shared resource state will be identical actually, and also because the update functions are the same or equivalent, then the classical, we can apply the classical I/O, and these will be indistinguishable. And now, if we would like to extend this beyond Clifford group circuits, well, the problem is that, so the reason all of this works is that Clifford is a normalizer of the polys. So by definition, it's just a matter of updating the exponents on these poly corrections. If we want to go beyond Clifford, then this trick is not going to work anymore. And namely, this is the relation that you get if you try to apply one of the non-Clifford T gates on x to the a z to the b. But in a way, we can use the following observation: the polys form a basis for the 2x2 unitaries, or n by n in general. So we can express the unitary correction as a complex linear combination of the polys. And then we can look at each poly and how it evolves as the circuit is being evaluated. And as long as the number of T gates is not too large, then this technique is still efficient. Namely, so we have this linear combination. So we're going to have classical functions that describe alpha 1, alpha 2, alpha 3, alpha 4 in this linear combination. This is for a single qubit. And if there are k T gates, then the function will output 4 to the k terms. Therefore, if we have logarithmic number of T gates, logarithmic in the circuit size, then we'll still have an efficient construction. So that's how we can generalize this gate teleportation idea and go beyond Clifford's. In the final construction, we're going to use techniques from quantum learning to give an indistinguishability obfuscator. And this is for a different family of circuits. They are the ones close to the Gottesman-Schwang hierarchy. So let me tell you what that is. We've talked about the poly group, we've talked about the normalizer, which is a Clifford, and let's look at a recursive definition of this type of normalizer idea. Let's C1 be Pn, and then CK is a normalizer of CK minus 1. So that would mean that C2 is the Clifford group, and then C3 would be the normalizer of C2, etc. So we know that actually we have universal quantum computation as soon as we are in C3. But to tell you the truth, the full power of the levels of the Gottesman-Schwang hierarchy in terms of computation is still an open question. We do have a learning method, this is due to Low, how to learn quantum circuits that are guaranteed to be close to the Kf level of the Clifford hierarchy. Learning here means that we have a black box access to a unitary V. That means that we can query it. We can give it an input state psi we're choosing, apply the unitary, and then observe something based on the output of this black box. So The task is to determine C such that the distance between C and some V is negligible. And here the distance measure that's used in this work of Low is a pseudo distance. It's defined here in this equation, and it's called a pseudo distance because if the distance is 0, it doesn't mean that the unitaries are the same. It means that they're the same up to phase, but that is insignificant in terms of unitaries. It's not something that we can observe. Okay, so that's the Gauss-Van-Turing hierarchy. And then this is the theorem of Low. Suppose that we have access to the unitary. When we're trying to obfuscate a quantum circuit, we have access to the circuit because we can run the circuit. We'll also have access to its inverse because we can run the circuit in reverse. So that means that we can apply a learning algorithm as the obfuscator. And then by definition, the learning algorithm does not depend on the way that the circuit is constructed. So its output will be indistinguishable no matter what equivalent input circuits we feed it. So then the challenge is just to describe in which cases do we get an efficient I/O. So if we take K being a constant, and that's the level in the Gauss-Van-Turing hierarchy, and epsilon being 1/2 to the K minus a half, then C will be unique up to phase, meaning that we'll find the same circuit when we run, no matter how we run this learning algorithm. And also the algorithm will be efficient. And that's what we're going to use as the QIO. Here is the definition of QIO that we simply need to adapt here in the case, because now we have a pseudo distance in terms of the correctness, namely 0.1, also called functionality. So where our functionality is that the output of the obfuscator, its distance in terms of the pseudo norm, will be negligible. The other criteria are basically the same. Efficiency is 0.2, and then security here, in fact, with this Low's approach, we get statistical indistinguishability. So that concludes our constructions. So we have the Cliffords, which are actually statistically secure. We have Cliffords with some extra T-gates, and that's computationally secure because we depend on the I/O. And then we have the one based on the learning, which is statistically secure, but correctness is with respect to a pseudonorm. The open questions would be to have to go for I/O beyond the classes of circuits that we have shown today, and also to find applications of QIO, because I think that that's going to ultimately define what is the correct definition and what are the interesting circuit families to obfuscate. Thank you very much.
So thanks, Anne, for the presentation. So if you have any questions, don't hesitate to ask them at any moment on the platform to the others, or any questions on the presentations or the papers. And they will be asked later on in the discussion session that we have after the presentations. So the third paper in this session is on forging Sphinx plus Haraka signatures on a fault-tolerant quantum computer. And this is joint work between Robin Berger and Marcel Thiepelt. And I believe Robin is giving the talk.
Everyone, my name is Robin Berger, and I'm going to talk about forging Sphinx plus Haraka signatures on a fault-tolerant quantum computer. This is joint work with Marcel Thiepelt. In our work, we analyzed the Sphinx plus signature scheme and each of its components. We found attacks for each of these components based on inverting the respective hash functions. We then investigated how we can use these attacks on each of these components to forge valid Sphinx plus signatures. In the next step, we implemented the Shake256 and Haraka hash functions in Q#. This allows us to estimate the quantum resources required for a pre-image attack on the hash functions, and therefore for forging Sphinx plus signatures using Grover's algorithm. We chose particularly Sphinx plus because of its position as an alternate candidate in NIST's post-quantum competition, and we chose particularly Haraka because it is one of the hash functions proposed for Sphinx plus, and to the best of our knowledge, it has not yet been analyzed in the context of a quantum resource estimate. I will start with a brief introduction into the Sphinx plus signature scheme. I will then follow up with the points of attack we identified for Sphinx plus and each of its components, And finally, I will give a brief overview of the results of our resource estimate for these attacks. Sphinx Plus is a hash-based signature scheme, so the core part of each component are hash functions. After computing the message digest of a message, Sphinx Plus consists of three different components: the forest of random subsets, or FORS, Winternet's one-time signatures, or WOTS, and the extended Merkle signature scheme, or XMSS. XMSS is a binary hash tree with each of its leaves being WOTS instances. The XMSS instances are organized in a hypertree where the leaf nodes of each layer sign the root nodes of the next layer. The leaf WOTS instances in the final layer of the hypertree sign the public key of a force instance, which then signs the message digest. A Sphinx public key consists of the root node of the hypertree, the Sphinx secret key consists of a secret seed, and a Sphinx signature consists of the force signature that signs the message digest and multiple XMSS and WOTS signatures for the hypertree. I will go into detail of each of the components when showing the attack on it later on. To sign a message using Sphinx Plus, we first compute a message digest from the message. We then divide this message digest into two parts: the actual message digest we want to sign and the position of a force instance we're using to sign it. Next, we're using this force instance to sign the message digest. In the next step, we sign the force public key with its parent WOTS instance and authenticate the public key of this WOTS instance with an XMSS signature. We repeat this until we arrive at the root node of the hypertree. All signatures together then make up the Sphinx signature for this message. When verifying a signature, we first compute the message digest. We then use this message digest in the corresponding force instance to compute a candidate force public key. Next, we go to its parent WOTS instance and use the WOTS signature and the candidate force public key to compute the candidate WOTS public key. We then do the same with its parent XMSS instance. This is repeated multiple times until we arrive at the root of the hypertree, at which point we have a candidate XMSS public key. This public key is verified against the Sphinx Plus public key. This is the only time a candidate public key is explicitly verified. All other candidate public keys are only implicitly verified by using them in computations of further candidate public keys. Okay, we're now going to look at how to forge a signature of each of the components of Sphinx and how to make up a forged Sphinx signature from a forged component signature. Our general attack scheme for forging Sphinx Plus signatures is to use two signatures, one valid existing signature and one invalid signature we created ourselves using a new secret key. We then select a position in the hypertree. At that point, we combine the top part of the existing signature with the bottom part of our signature. As this new signature is invalid, we attack the Sphinx component at that point, so it authenticates the public key used for our signature for the public key used in the existing signature. This means that when verifying this part of the signature, the computed candidate public key is equal to the public key used in the real Sphinx instance. We need to make sure that the component we selected is present in both the existing signature and in our signature. However, for most of our attacks, this can easily be achieved. This procedure results in a valid Sphinx signature, because when verifying it, all computations done starting above the point where we combine the two signatures are the same as when verifying the message with the given signature. Before we go into detail about the attacks on the Sphinx components, which are all based on a preimage attack on the used hash functions, I want to quickly explain how we find these preimages. Assuming no structural attacks on the hash functions, we use Grover's algorithm to find preimages. We use our Q-sharp implementation of the hash functions to instantiate Grover oracle, and then we can apply Grover's algorithm to qubits initially in uniform superposition. In the end, we receive qubits which can be measured to a preimage of a given value of the hash function with high probability. Using this, we will now go into detail on how our attacks on the components work. In our paper, we selected the 2 most interesting attacks on the Sphinx components. However, the extended version of the paper that will appear on ePrint will contain an attack for each of the components. In this talk, we will go into detail on 3 of these components. Here is an overview of the components in Sphinx Plus we can attack, which are the message digest function, the force, WOTS, and Xmss signature schemes, with the message digest function allowing an existential forgery attack, and the attacks on the other components allowing a universal forgery attack. Some attacks require evaluating the hash function multiple times recursively in the Grover oracle, therefore increasing the size of the quantum circuit for finding the preimages. Some attacks require multiple preimage searches, also affecting the quantum cost, while other attacks require only a single preimage attack with recursion depth 1, like the attack on Xmss. In the following, we will go into detail in the force, WOTS, and Xmss attacks. We will not go into detail about the message digest attack, as it is not particularly interesting, and it requires a larger input length and is therefore by far the most inefficient attack of the ones we listed. We will start with the attack on force, but let us first look at how force works. Force consists of multiple hash trees, with the leaves of the hash tree being pseudo-randomly generated secret values. Each hash tree signs a block of a message digest, where a signature for a block consists of a secret value of the tree, along with its authentication path. In each tree, the position of the secret value to be used depends on the value of the message digest. A signature for the entire message digest consists of a signature for each tree. The authentication path consists of all sibling nodes of nodes from the path from the leaf to the root of the tree. The hash of all root nodes is the force public key. A signature is verified by recomputing a candidate root node from the secret value and the authentication path for each tree, computing a candidate force public key, and then verifying this candidate public key against the real public key. To forge a force signature, we select all values in the signature at random, except for the topmost node in the authentication path of the last force tree. In this picture, that's S1. This fixes the root nodes of the other trees, R1 to Rk-1, as well as the value S2. We then adjust the value of S1 so that computing the root node of this hash tree, Rk, and then using this root node to compute the public key, results in the real public key. To do this, we apply Grover's algorithm using a recursive application of the hash function. A recursion depth of 2 is necessary, as the first application of the hash function computes the root node of the tree, and the second application computes the force public key. While a lower recursion depth is possible, this comes at the cost of the amount of preimage searches required. We will come back to this trade-off during the attack on WOTS. The next attack we are looking at is the attack on Winternet signatures. Similarly to the force signature scheme, WOTS signs a message by first dividing it into multiple blocks, and then signing each block individually. To do this, for each block, WOTS uses a hash chain, where the first value of the hash chain is a value pseudo-randomly generated from the secret seed. The public key of a block is the last value of the hash chain. The WOTS public key is the hash of the public key of all blocks. A message block containing a value I is signed by revealing the ith value of the hash chain. A signature for a block is verified by using the signature to recompute the last element of the hash chain, obtaining a candidate public key. This candidate public key is then verified. Our attack works as follows. When forging a WOTS signature for a new message, we forge a signature for each of its message blocks. We assume to already have a valid signature for a different message. To forge a signature for a block, there are 2 cases. If the value of the message block is greater or equal to the value of the message for which we already have a valid signature, we can use this existing signature as a starting value of the hash chain and advance in the hash chain by the difference of these values. This results in a valid signature for that block. If, however, the value of the block we want to forge a signature for is smaller than the value of the given signature, we need to go back in the hash chain, meaning we need to find preimages. On average, this difference is 5, meaning that on average we need to go back 5 times in the hash chain, resulting in a hash function recursion depth of 5 in the Grover oracle. As mentioned in the previous attack, we can do a trade-off between recursion depth and the amount of pre-image searches required. Instead of forging a signature for each message block, we could also use random values as signatures for these blocks and only do one pre-image search for the last block. While this does not result in matching block public keys, it does result in a matching what's public key. While both approaches are possible for attacking both fors as well as what's, the chosen approach has other effects as well. In this case, for example, the approach we chose also influences the success probability. For doing a pre-image search for each block, as we proposed for what's, it is guaranteed that such a pre-image actually exists. While doing a similar approach for fors, a pre-image might not exist for a given public key and recursion depth. The Xmss scheme consists of a single binary hash tree authenticating what's public keys. The Xmss public key is the value of the root node. The Xmss secret key consists of the secret keys of the what's instances and its leaves. To authenticate a what's public key with Xmss, the authentication path for the corresponding node is calculated. This authentication path makes up the Xmss signature. A signature is verified by using this authentication path and the what's public key it authenticates to recompute the root node of the tree. This root node is then verified against the Xmss public key. To attack the Xmss signature scheme, we need to find an authentication path that, when used with a different what's public key, computes to a given Xmss public key. We achieve this by choosing all values in the authentication path at random, except for the topmost node in the authentication path. In this image, this fixes VL. Then, we choose the topmost node in the authentication path, VR, so that computing the value for the root node results in the given Xmss public key. We only need to evaluate the hash function once from VR to get to the public key. This means that to forge an Xmss signature, we need to do a single pre-image search with a recursion depth of 1. Now where we know how Sphinx and its components work, and now how we can turn a pre-image attack on the hash function into forging signatures for each of its components, we can look at the resources required for actually carrying out the attack. Sphinx Plus offers parameter sets for 128, 192, and 256 bits of security, achieving NIST security levels 1, 3, and 5 respectively, while Sphinx instantiations with other hash functions can achieve up to security level 5, the Sphinx Haraka instantiation is limited to security level 1. This is because of the limited capacity of the used sponge construction, where a collision on the internal state of the hash function can be used to find a pre-image or second pre-image. This allows even a classical attack on Haraka in about 2 to the 128 steps on all parameter sets. This is the reason why we limited ourselves to the 128-bit parameter sets for the resource estimate. For our resource estimate, we followed the approach of Jones 2012, making currently established assumptions on the performance of quantum computers and optimizing magic state distillation for our use case. The most important assumption we made for our resource estimate is that the resources required for a quantum computation on a large-scale quantum computer is sufficiently well approximated by a quantum computer using surface codes. This allows us to concretely calculate the overhead when projecting logical resources to physical ones. The second assumption we made is to estimate the amount of physical qubits required to embed each logical qubit in the surface code. This assumption is based on Gidney 2021. Our third assumption is to estimate the error rate of physical quantum states and quantum gates, as well as the amount of time required for computing one surface code cycle. This assumption is based on Fowler 2013. After making these assumptions, we chose some cost metrics to estimate and compare the resources required for our attacks in a meaningful way. The first cost metric we used is the amount of physical and logical qubits, which represent the spatial requirements. The second cost metrics we used is the amount of surface code cycles. This represents the time required to carry out our attacks. Our third and final cost metrics are the logical qubit cycles. It represents the space-time product. It is the product of the amount of logical qubits required for a computation and the amount of surface code cycles required. Amy 2017 have claimed that the classical resources required for error correction on one logical qubit on one surface code cycle is roughly equivalent to the classical resources required for evaluating a hash function once. We believe that this is a fitting cost metric, as it allows us to compare the quantum resources required for carrying out one of our attacks to a generic classical attack in a meaningful way by only comparing classical hash function invocations. Knowing how we evaluate our attacks, we will now look at our results. We will only show our resource estimate for the attack on Xmss, as it is the attack requiring the fewest resources in all of our cost metrics. We'll start with the amount of logical qubits required. For the shake hash function, we need about 24,000 logical qubits, while the attack using Haraka only requires about 2,000 logical qubits. Transitioning to physical qubits, the attack on shake uses about 8 million physical qubits, and the attack using Haraka requires about 2 million physical qubits. In contrast to the amount of qubits required, we can see the opposite happening with the amount of surface code cycles. The attack using shake requires about 2 to the 84 surface code cycles, whereas the attack using Haraka requires about 64 times as many surface code cycles with 2 to the 90. This is because our quantum circuit for Haraka has a smaller width than the quantum circuit for shake, but it also has a higher depth. Since the amount of quantum gates for each of the quantum circuits is roughly equal, it is no surprise that the same holds for the amount of logical qubit cycles. Here, the attack using shake requires about 2 to the 99 logical qubit cycles, whereas the attack using Haraka requires about 2 to the 101. This means that a classical attack requires about 2 to the 28 times as many classical resources as our quantum attacks. To conclude, we looked at the Sphinx Plus signature scheme and each of its components, we looked at attacks on each of its components, and we found a way to use these attacks to forge valid Sphinx Plus signatures. We then implemented 2 of the hash functions used in Sphinx Plus in Q#, and used this Q# implementation to estimate the quantum resources required for carrying out the attacks we found earlier. We found that the attack using forged Xmss signatures performs best with a logical qubit cycle count of about 2 to the 101. Thank you.
Thanks, Robin. So as I said before, if you have any questions, please ask them in the on the platform. And thanks, of course, to all the speakers for the presentation. We can now begin with the discussion question and answer time. Yeah, so if you have any questions, you can still ask them in the platform. Don't be shy. You don't have to ask them live anyway. This is me who is reading the questions. So I believe Anne had a question for Xavier to begin with.
Yeah. Yeah. Hi, Xavier. Thanks for your presentation. I was wondering if you'd like to kind of clarify the attack model. It looks like for the quantum queries, you're looking for CPA. But what's the attack models for the different algorithms?
Yeah, so it's quantum queries, and it's technically chosen quantum queries because we need to query multiple times the periodic function and the uniform superposition input. But besides that, I don't know if there is really some meaningful work with known quantum queries in that kind of setting. There is one exception, which is for the offline Simons algorithm. In that case, we only have classical chosen queries, chosen plaintext. So in that case, we have a quantum attack on classical data.
But you need superposition access to the...
No, and not for the offline Simons algorithm. For this attack, you don't need superposition access. You only need classical plaintext ciphertext for the secret function.
Okay, thanks.
Okay, so since Anne was asking a question, no, I will ask a question to Anne. So you have a construction of QIO for Clifford circuits, and then if you add just a few T-gates in there, it's still like gives you a construction that still works. And you said that the count of T-gates must remain logarithmic. I wanted to know what happens. Maybe this is a dumb question, but what happens if I replace the T-gate by any other non-Clifford gates? Does it still does the same result that you say still hold? And I don't know. Could it still like it could be some improvement in, it could be some optimization, for example, to have a quantum circuit where your non-Clifford gate is not the T gate but something else. And you use your construction of QIO in this setting. I don't know.
Yeah, that's a good point. We didn't consider that. It's just the T gate is so common and it's very simple and it has that nice equation and relation that you need the P correction. But now that you mention it, if you have a different type of circuit architecture and you have a different non-Clifford gate, I would conjecture that you can get a similar equation, slightly more complicated, but it also won't. Like when you try to commute the new gate, we'll call it I don't know, T star. Try to commute it through a Pauli correction. I'm guessing you're going to get one extra term, and you can compensate for that in the same way, I would say. But
okay.
Yeah,
it was keyword.
Yeah.
Okay.
Yeah, I think so.
Asking for a friend. Okay. Thanks. Okay, I wanted to ask also a question to Robin. By the way, I think I called you Robin, but it's French way, so Robin, I guess.
Mm-hmm.
So whenever you attack on XMSS, there is one of the improvements that you have over the very basic oversearch. Is that so when you attack when you do the pre-image attack on Haraka, this is a small sponge construction, so you need to apply the permutation twice, and you say, but we only need to apply it once in the quantum circuit. We can pre-compute the first iteration of the permutation. I wanted to ask whether you think, with all the optimizations you did and all the work you did on optimizing this attack, there could be other improvements of this nature, like having some small parts pre-computed and reducing the total quantum overhead on these attacks on Sphinx Plus? Or do you think you really reached the bottom of it?
On the attack itself, I don't think you can optimize a lot more. We looked at the sponge construction and how to only compute the minimum you need to compute there. And for the attack, I don't think you can optimize more. Where you can optimize, or where I think you can optimize, is to use a more efficient implementation of the hash function. I mean, we optimized, we implemented the hash functions in Q#, and we tried our best to optimize the hash functions as best as we can, but I don't think we used the most efficient implementation of the hash functions.
Okay.
There might still be room for improvements there.
Okay, thanks. We have a question from, and this is also for you, Robin, from Francisco Rodriguez Henriquez. And he's asking, so it's saying, thanks for the insightful talk. And he's asking why Haraka requires more depth than Shake 256?
That's a good question. The main reason is that the most expensive part of the computation is applying the T-gates. And in the Haraka hash functions, a lot of the qubits, the T-gates are applied to. There's a lot of dependencies on gates for further computation. So we have to compute one thing before we can compute something else. And with the Shake hash functions, we can do more of these computations in parallel. So there's still roughly the same amount of T-gates, but they are distributed in a different way.
Thanks. I hope this, again, answers your question. So we have yet another question for Xavier this time. So So in your paper and your presentation, you showed that when you have this, when you're applying Simon's algorithm to a function, you can usually truncate the output of the function to like a really small amount of bits compared to what you would have needed in this standard Simon's algorithm. And there is also another paper by May and Schlipper who did basically a hashing of the function output. And apparently if the hash function is good, you can hash down to a single bit and Simon's algorithm still works. And I would like to ask, obviously this is going to the same direction, but do you think there could be a connection between what you did and what they did, and I don't know, basically truncate to 1 bit in a full general setting, or what could happen?
So indeed, what I've shown is that you can reduce up to logarithmic amount of bits without increasing the cost. And what they've shown is that even with only 1 bit of output, it's not that bad, because on average you will multiply the query cost by a factor of 2, something like that. And indeed, in fact, we have 2 slightly different approaches, and if we try to use my framework to the 1 qubit case, you won't get anything meaningful. But I think there should be something that could allow more interesting trade-off, especially for the offline Simon's algorithm, because you would have like a few hundreds of parallel calls to the same oracle. And if you can gain 1 or 2 bits, then it might be worth it in terms of memory cost, even if you had to do a few more queries. So there might be some way to gain this way by using a slightly different approach.
Thanks. So I also wanted to ask yet another question, maybe to Xavier. So there is also in your presentation you said that Simon's algorithm works well against it works well in Simon setting when you have a periodic permutation, basically. But you can also create functions that are periodic and on which it doesn't work at all, because basically you're trying to solve a very difficult problem like curve search. And do you have an intuition on what happens in the middle case? I have a function that is, well, not an extremely bad case, but not an extremely good case either. Somewhere in the middle, does something happen, or are we completely?
Well, what I've shown is that the bad case is actually extremely rare. So for most notions of middle case, you will actually just be in the good case, because there is almost no chance to have some collisions that are so bad that Simon's algorithm is impacted. Technically you could still construct some functions for which it would be pretty bad, but they would still be quite degenerate, and this is not something that would occur randomly. But yes, technically you can have some less extreme cases than what I presented, even if they will be quite bad.
Okay, but in general there are no bad cases.
Yeah, they don't occur in practice. Right. That's the main thing to remember.
So on this very good perspective, I think we can end this question and answer session. Thanks to the 3 of you for the presentations, for being here. We're now going to have a half-hour long break, so you can take a coffee or can take a tea depending on your time zone. The next session is the invited talk by Lucas Defeo at 10 a.m. who is going to talk about the what's next for isogenic-based cryptography. So please be here to listen to Lucas at 10 a.m. And for now, we are having a break. Thank you.